face that Extem will take and in a Bayesian probabilistic manner actually give you the space group. So that's actually at least it gives you the extinction symbol from which you can actually get the space group, and it ranks it in a proper probabilistic manner. And Anders has to take a huge amount of credit for that. And JPowder, and this is something that Anders has done, but with Ken overseeing the project. And here's another website that's interesting and is continuously developing, and it's free software. And again, I take a copy of that as www.jpowder.org, and that's constantly being developed. So that's Anders, and he does it all just nice and relaxed, cool, and laid back, actually. So there's the great man up there. The genesis of Dash, actually, and there was a question the other day about do you do genetic algorithms, do you use swarm methods, do you use simulated annealing? And the story started, actually, after the structure determination from Powder's meeting, and Ken and I were doing a very different things. I was actually pushing the Patterson function and various things like that, and Kenneth with Tony Choke actually started up this global optimization approach, actually, because people like Yuri Andreev and Ken Harris and Peter Bruce were involved in doing that, and there was an interesting paper. Kenneth and Tony actually went down the genetic algorithm route, and I was Ken's boss at the time and just let him get on with it, and I think that's a very good thing for a boss to be able to do. It looked as though he was heading down an instant direction. It wasn't his job at the time, but he had the freedom to go on and do that. I take the credit for that, but also for having, we had a dialogue, and Ken went into very sophisticated GA algorithms that involved populations, where you had multiple islands and you had all this crossbreeding, and he indicated that in a single slide, but there was a lot of work that went into that, six maybe a year's work of thinking about it. And I said, I'd done work in simulated annealing before, and I said, I just think it's going to be a more reliable, a better technique. And Ken mentioned in 1999 that we had a statistician at the IUCR Congress in Glasgow who basically said, when the chips are down, you want to go for simulated annealing. It's nothing like as sexy as genetic algorithms. And so we went in parallel at that point, and I began developing the simulated annealing, and Ken and Tony started on the GA, and the simulated annealing just outperformed it. And I take my hat off to Kenneth, because he said, okay, right, I'll park it. And we went on from simulated annealing there, and that's the paper back in 1998, and this is the godfather, Kenneth's older brother, and the three of us published that paper back in 1998. And so I've mentioned about this effective global optimization algorithm, this parallel tempering. There are variants of simulated annealing that probably are more powerful, but they both get there, and there might be a factor of 2 or 3 difference in performance. But you get stuck more often, and that's certainly our experience if you use GA. In fact, actually, we couldn't even solve things like ibuprofen easily. So the simulated annealing, and that's one of the things, you have to have an effective global optimization algorithm. And Kenneth, being the chemist, had already, we'd realized that we needed to connect it up, and Yuri had actually chosen something that wasn't the Z matrix, it was something else, but Ken basically imported this from, was it Gulp or something like that? Was it one of the molecular dynamics programs? I can't remember now. So we had a way of reducing the number of parameters, and again, Ken and I have already mentioned that, and that's important to be able to do to get down to a manageable space. And I guess my main contribution was to realize, in fact, that you could go to these correlated integrated intensities. And at that time, actually, that gave us a factor of 1,000 speed up. We went from 1 every 3 seconds to 350 a second on exactly the same problem. And that allowed us really to get going. And basically, that was between 97 and 98 that we did that. So we were using, just simple clusters. Well, actually, at the time, not simple clusters. 1999, it was fully ported to Windows. And then from 2000 onwards, it's been marketed by CCDC. In fact, actually, Ken and I felt a little bit awkward about saying this, but we wanted to tell the history because there's an interesting story in this, actually. And Peter Stevens has just come from New Orleans, where he chaired a session in memory of Lachlan. And Lachlan, was great in many ways, but he did something, actually, that I have to say, it did upset us at the time, actually, because the Rietveld mailing list was really quite aggressive in those days. And And Lachlan and Armel and others basically simply did not believe the paper that we published. We published the results, and somehow we cheated. And in fact, the most polite thing that he could do was to call us Mystic Druids. And of course, you can't really, and certainly Kenneth and I wouldn't do it, is to get into an argument on the Rietveld mailing list. So we stayed silent, and silence actually is sometimes taken as an indication of guilt. But we took two approaches, and I'll say that the first one was we actually called the program PC Druid. So we called it Druid. And the second one, actually, is that we basically took on this challenge that Armel Lebey actually came up with shortly afterwards. And in fact, I'm going to show you this very briefly, partly because this is a book that everybody should read. I think it's one of the most important science books of the 20th century. It's the logic of science. It's all to do with probability theory. And at the end of the day, all that we're doing is actually coming down to looking at what's the most reliable, what's the most likely solution to the problems. And here's the great man, Ed Janes. And again, I'll leave that up just for a moment. Do write it down, and it's worth just dipping into it. I'm going to go to chapter 5. And chapter 5 actually is queer uses for probability theory. And it was Devinder Sivia who, is one of the great Bayesians who pointed me to this. And it actually, in fact, it brought quite a lot of comfort, because in here there's a story about Laplace back in the 1800s, and he didn't believe that meteorites existed. He said, how on earth can stones just fall from space? And of course, there were people, peasants, who said, no, it happens, it really happens. So for one familiar with the laws of mechanics, the notion that stones fall from the sky seemed preposterous. But there was a fall in 1803 which left fragments studied by Bio and other fresh scientists who changed the opinions of the educated, including Laplace himself, so he moved his opinion. In this case, the uneducated, avid for the marvelous, happened to be right. C'est la vie. Okay, so actually what James says in his book actually is that curiously, when they were writing the book, he found himself a victim of this as well. One of his students, Greg Bretthorst, actually in chapter 21, they talk about this work that they did with Bayesian analysis to estimate the frequencies of non-stationary sinusoidal signals such as exponential decay in NMR data. And we found, as was expected, an improved resolution over the Fourier transform method. And this is all sort of things that we know about. We know about actually that from the maximum entropy side of things. If we claimed a 50% improvement, we'd been believed at once, and others would have eagerly adopted the method. But in fact, we found orders of magnitude improvement, as did we. It was, in retrospect, foolish of us to mention this at the outset. For in the minds of others, the probability that we were irresponsible charlatans was greater than the probability that a new method could possibly be that good. And we were at first not believed. And when Devinder said that, I thought actually Lachlan was right. It just seemed so improbable to publish a paper that said that we were doing things 1,000 times faster. And we were right and accurate. And in fact, I should say that others followed very quickly. Fox and in fact Anders spent a lot of time talking with Vincent about that. Powdersov, and I certainly spent a day or so talking with Gerhard Engel from Acceleris, talked to that. And Peter Stevens didn't bother talking to us at all. He said, well, if these guys can do it, so can I. And that's exactly what he said to me. Anyway, we basically, over the years, and we're standing here now, actually, just over 10 or 12 years later, and everybody believes it. And so, it was, I think it was fair for Lachlan to do this. And of course, we had this test, and we were participant 2. And we solved the problem, and from download to submission actually was 6 hours. And we wanted not only to, I guess we were trying to prove a point actually, not only that we could do it, but that we could do it quickly. So there's the Druid program, as we were calling it, actually doing the job. So that's the history, and I'm going to pass over to Ken now, and he's going to go through these basic things step by step and take you around the version of the maze that we use in Dash.
Swap.
And you get this one.
Good. So just wait 1 second for the mouse to warm up. I think the fact that that took so long to install means that I need a new laptop. It's, as you'll hear from my talk on the final day, one of the great debts that I owe both to Chris Gilmore and to Bill is for telling me that computers can never be fast enough. We used to have a group motto which was to spend, to save, which meant that we always bought the fastest PCs that we could. And in fact, the reason I mention that is a combination of a fast PC. You can have the fastest PC, but if you don't have a good core engine for it, then it's really a bottleneck. And Dash certainly does have a very fast core engine, which is, of course, why it's called Dash. So what I'm going to do is actually, there's plenty of time in the workshop to go through the tutorial examples that are supplied on the memory stick and are installed when you install Dash. All I'm going to do is do a quick walk through one of in fact, the first example, just to illustrate some of the features. And I'm going to invite Bill at certain points to comment on some of the control parameters that we don't normally touch, but just to illustrate some of the flexibility. So Dash is fired up. We're just about to load in some data. And the data set, if I can remember where I put it, should be here. Tutorial1.xy8. Now, this is actually a data set that I collected many, many years ago at Brookhaven on Dave Cox's beamline. And it's of a molecular organic structure called hydrochlorothiazide, but more of that later on. So you can see we've loaded the data in. You can do all the usual stuff of zooming in and scrolling along and zooming back out again, but that's not particularly interesting. So we'll skip on to the next one. In this case, this is where you get the chance to tell the program what kind of radiation you're dealing with. In this case, it already knows because there's a single line at the beginning of the XYE file, which is nothing more than a wavelength. So when it sees that, it works out that it's actually synchrotron data and sets the appropriate corrections. So if we look down, we'll see that there's a little bit of structured background, and Dash actually gives us a chance in a second to fit that and get rid of it. The first thing it does is, I mean, this is not a hard and fast rule, but generally speaking, we find that certainly with microorganics, if you work to a data resolution of roughly 1.75 angstroms, then that's a good balance between having enough resolution to pin down the structure accurately, and that's particularly true of flexible structures. That constraint can be relaxed for planar type structures. You can work with much lower resolution data, but as a rule of thumb, this is a reasonable compromise. And by going to that approximate resolution, it keeps the number of reflections that we're using down to a fairly small number. And speed is a function, at least in Dash, of number of atoms and number of reflections. So this seems to work very well, so we'll just accept that. And so when I say next, it's going to truncate the data to 1.75 angstroms. Now, as I mentioned, we have a background in here, and there are many ways that we can deal with the background. We can just go ahead and refine it as a polynomial in the poly refinement when we come to extract intensities. But as I indicated earlier on in the global optimization talk, particularly at high angle where overlap is severe and maybe the background is quite highly correlated in with the intensities, if you can remove the background a priori, it makes the poly refinement a little bit more stable and a little bit more reliable. So, Bill, would you like to comment on some of these background removal terms?
I mean, just briefly to say, actually, that this is, I guess, one of the first stages where you might see something very different. You've seen some of the diffraction patterns with relatively sharp features in the background, some with very broad. And these window numbers there, they're basically what we most commonly see in terms of the smoothness of the background. 200 corresponds to 200 data points, and we're actually going to go in there and do something that's sort of smooth on that level. If we had something that was highly structured, we might reduce that number. And so effectively, these are just parameters, and there's more information about them. I don't want to stop you in your flow, but there is this flexibility at that point. So if you don't put the right number in, you can go back and just get it to the point where you're visually satisfied with the fact that the point there, so that's on defaults, it just goes straight through there, we can carry on.
So as you see, all I did was hit the preview button, and you get a preview of what the background is going to be, and that's about to be subtracted. That's as Bill was always very fond of, good enough for government work. So we shall apply that and move forward. So the background's now been removed. So the next step is indexing, and we actually use the core of the DICVOL program. It's actually now built into Dash, courtesy of Danielle. We should, of course, have said that, actually, courtesy of Danielle. And there are two ways of doing this, and what I'll do is I'll take the easy way out and do the auto-select of peaks, but in the tutorial, you can actually find that you can go in and fit peaks individually just by zooming in on them and sweeping out and then hitting the Enter key, and it fits them. And that can be useful where there's any sort of ambiguity. Now, being a demo, fortunately I have done this in advance and I know it works, although being a computer it may well come back and bite me on the bottom. So I will hit auto-select peaks. So you see there was a selection that was done which is based on a simple intensity threshold. Then there was a slight pause, and then it flickered again. And so what it did was it initially picked those peaks, so it just did automatically what we would have done manually, but then it went a little stage further and actually fitted them with a void profile. And in order to get that fairly robust, it actually uses a simplex algorithm to do the fit. So that gives us very, very accurate peak positions. And we heard from Professor Virtual Stevens, who is now with us. Oh, can I just point out, for those of you that attended Peter's excellent lectures on the first day that were delivered electronically, he is now here. Peter, can you wave up? So, welcome. Hey, let's... So, okay, so thank you for that. And Peter emphasised the importance of getting peak positions accurate, and by fitting the peaks individually rather than just going to the top, we get them accurate. So there, they have been fitted, and I will just hit next, and it flicks up a little DICVOL control window. I'm going to turn off triclinic because it simply slows things down, although not by much. We'll hit the run button, and that's the index. And as you can see, Dave Coxery's beamline very well set up. Not much to complain about there in terms of the M and F figures of merit that we've heard about previously. And if you really want, you can view the original DICVOL output. Sometimes that's quite useful if there's more than one solution. Now, I happen to know the rough molecular volume for hydrochlorothiazide, so I know that that volume sorry, I'm pointing at the screen. I know that that volume here for the cell is chemically sensible, and with these figures of merit, really, there's no reason that we can't accept that. Since there's only been one solution thrown up here, then it has been automatically imported, and you'll see the tick marks there corresponding to the reflection positions. So, there we go. What's next? Well, we could go ahead and do a poly refinement on this, but we'd be doing it in space group P2 because as of yet, we don't actually know what the space group is. So if you knew what the space group is, you could simply pop it in, but I'm going to illustrate the use of the XSIM core within here. We heard Angela talking about the probabilistic way of determining extinction symbols in the Expo talk. We'll show how we do it here. So I click space group, and the first thing it needs to do is to do a polyfit in the group, the space group that has no systematic absences. Now, ideally, we want to fit the profile as best as we can to get as many accurate intensities as we can to inform the decisions that we're going to make. So normally if I was doing this myself, I would hit the clear peaks button. That would clear all of these previously fitted peaks. And then I would go through and select 2 or 3 peaks to get a good description across the pattern of the peak width, and then I would start refining. However, I know that these peaks actually have already got quite a good sampling. We've modeled the peak shape well, so I can just go straight on and do the poly refinement. And actually, that's the poly done, and that's good enough. That's more than good enough. So there's little ripples there, but I think you'd agree that we've fitted the pattern pretty well. You can play around with the peak shape parameters and improve the fit, but again, we'll leave that for the workshop. And so having poly fitted in P2, I now just hit the run button, and the analysis of the likely extinction symbols is popped up for you in ASCII form. Bill, do you want to say a little bit about that?
Well, again, just very briefly, this is a bit like going to the races. It's like horse racing. At the moment, you're basically betting on what's the most likely outcome. That factor of 7.6, 8 is saying that the P21 symbol here is e to the 7.68 times more probable than P2, and everything else is just so improbable it's not worth saying. So the data, basically, we've inquired of the data and say which is the most probable solution, and it's coming back and it says basically at the 99.9% level, it's P21.
Okay. Of course, there may be cases, as Angela outlined in her talk, where things are not quite so clear-cut, and you may have to test, if you have similar probabilities, you may not always end up taking the top-ranked one, but in this case, you would be foolish to bet on anything other than P21. And I may be foolish, but I'm not that foolish. So I'm going to go back and just select P21, apply that, and then just re-refine. So everything looks quite happy there.
Can I just say a comment there, actually, that those of you who saw the chi-square there, in fact, actually previously it was 2.875 for P2, and now we've taken a peak out, it's 2.875. It's basically stayed the same. If it were, again, if that were to change, that's a thing to flag concern, actually, if it suddenly went a lot bigger.
Okay, so we've now fitted the data, and we have, although you can't see it here, a list of HKLs and reflection intensities and their ESDs. And so you get the chance to save that fit, and it gets written out as something called an SDI file. I think it's lost in the mists of time exactly why it's called an SDI file, but that's largely unimportant. So we're now at a stage where we can actually read in a model and do some solving. So being a molecular organic, I know in advance what the bond lengths angles are likely to be. I don't know the conformation. So I need a molecular model, which I'm going to read in, and you'll find when you load things up that there is in fact what's called a mol2 file, which is just a molecular model description of the material. And when I read that in, Dash analyzes it and automatically creates a Z matrix version of that. So it automatically looks at the molecule, figures out where the flexible bonds are. Now you can see it's calculated there are 7 degrees of freedom here for this particular fragment. That's the 3 positional, 3 orientational, and 1 twist angle in the molecule. I'd say in general it's pretty good actually at figuring out what is and is not allowed to flex. Occasionally it'll encounter something where you know better than it does, so you can go in and edit the Z matrix if you really want to, but we won't go into that just now. I'll just point out that if you suspect there's preferred orientation in your sample, you do get the chance to include a preferred orientation axis, and we have a refinable parameter associated with that, and that actually works really rather well. In this case, we've got good transmission capillary data. We don't actually need it. We can click on the View button, and Dash, being a CCDC product, actually is very well linked in with some of their software. So that's the mol2 that we have used to generate the Z matrix, just displayed in Mercury. So I'll tuck that away for the moment. Next up, you get a chance to fix some parameters. Now, you might think, we're in P21, he's going to fix the y-axis or fix the y-coordinate of the fragment. Doesn't make a blind bit of difference in global optimization. We can skip over that. There's some stuff here to do with database constraints. Again, happy to chat about that later on. Not really relevant at the moment. You'll see the tick box that says randomize initial values. That means that any value, for example, of a torsion angle that's been read in from our initial molecular conformation is completely ignored and it's just randomized. Okay, this is probably the most important thing. Bill, 1 minute, do you want to say anything about the control parameters before I hit the run button?
Golly, I've forgotten. I mean, basically, if you look, T naught is sitting at naught at the moment. That's basically, the temperature at which you're going to do the beginning of the simulated annealing. Now, temperature is not a real temperature like boiling a kettle. This is a temperature that's in units of chi-squared, our target function. And so, what we're going to do actually is that we're going to do an initial test where we're looking at 100 or so trial structures, and that will allow us to decide what T naught is. And then we're cooling, and basically what that's saying is that after every sequence of runs, and you can see for the moves each temperature, we've got 4,000 there, we're going to drop by 2% each time. And again, you can do that faster or slower, and we found that sort of 2% is slightly on the conservative side, but if you've got some of the bigger problems, it's a better way to start off. And the number of essay runs, simulated annealing runs, it's saying, you never do one. You're starting off at a single, you're not starting off and doing a single run. Ken showed you with the famotidine example in his talk that you do 50 or so runs, maybe a couple don't work, but you come down, hopefully, to the solution more than once.
Okay, thanks. So we have 3 ways of terminating things. First of all, the number of runs, as Bill has just said. We can set an upper limit on the number of simulated annealing moves. For this example, I've just set it to 1 million. And we have this profile chi-squared multiplier. If you remember in the global optimization talk, I said one of the nice things about doing powder diffraction is you know what your best target value is. We know what the best target is. We're not going to fit any better than we did in the poly. And so what this little control parameter here says is, okay, once you get within a factor of 5 of the recorded poly version, call a halt, enough annealing. And in fact, it then invokes a simplex to pull us down to the global minimum very quickly. So we're going to do 5 runs, and I've set the profile multiplier at 5. Final set of options that gives you different treatments for hydrogen. You can either treat them explicitly, which is slightly slower. You can ignore them, which speed things up. The absorb button is a sort of compromise between the two. This thing here that says auto-local minimize invokes the simplex at the end of the simulated annealing. We'd always recommend leaving that on. It doesn't do any harm at all. We use crystallographic center of mass for positioning. If you know where a particular atom happens to lie, you can untick that box and force it to go to a particular position. So without further ado, we hit the solve button, and that's 1, 2, 3, 4, 5 times solved. So 7 seconds to solve them, and we'll see that we have 4 identical answers and 1 that's just a little bit off. So let's unclick that and show an overlay of the top 5. And what we should find is, just as a click between the different solutions, they're all absolutely identical. There's absolutely no surprises there, and we can examine the structure in mercury and start to look through and see if the packing makes sense and if hydrogen bonding patterns make sense, and you take it from me that they do in this particular case. We can look just out of interest and compare one of the ones that got stuck in a slight local minimum, and if I do an overlay there and just flick between the two, if you watch the group at the top. In fact, I alluded to this the other day about the possibility of an SO2 NH2 settling into an alternative minimum. You'll see that all that's happening really is a slight move in the molecule and that group at the top twisting round. If you got that last solution, you could easily fix it out. You'd notice the hydrogen bonding patterns were not the same. So that's really, I'll stop at that point in terms of demoing a solution. I'll just show one more feature that we can go back here. Obviously, that was a trivial example that we knew would run in time. I'll just point out another feature that we developed originally for running on a grid MP system, which is a distributed computing system. Those of you that are familiar with the program SETI at home will know the context of that, the idea that if other people aren't using their PCs properly, well, we'll send jobs out to do them. So imagine that you had, say, more runs to do, and that they were going to be significantly longer, maybe 10 million moves then, and you're going to do a lot of them, then you get the chance to actually create a batch file. And so I could say, for example, that I want, say, 50 runs, and I want them written as individual control files that I can then distribute out to a grid. So I'm going to write that batch file. Okay, so that's a set of batch files written for the grid. Now, hands up everyone who has access to a copy of Grid MP. Bill, show some support. Put your It's the most fantastic system. It's absolutely amazing, but of course, it's used mostly within financial institutions and some pharmaceutical industry. It's not the sort of thing that you have sitting around in many university departments, although some university departments may have a system called Condor, which is a free, very similar thing. But what you may not know is that if you have a copy of Dash working away very quietly in this directory down here called unsupported extras, you'll find something called mdash, which is something that basically can read the grid file. And if we look at the configuration, you'll see that it recognizes that this PC here has 4 cores. Actually, it doesn't technically, only has 2, but it picks up hyper-threading and thinks that it has 4. And that gives you the chance to actually run this grid file on a multi-core engine and speed things up substantially as a result. So that you don't tie your machine up completely, we can run it low priority. So the Dash jobs get set in the background at low priority, and you can continue to work on it. So just to illustrate that, and then we can draw a line. It's always nice to see. So as I hit the start button, then we should just be able to watch the CPU usage rank up. And there we go. So we've got all 4, in this case 2 real, 2 virtual cores running flat out. And this scales up to, I think I've had 16 cores running, and it runs very, very well. Now, there's nothing particularly smart here. As I'll mention in the talk at the end, this falls into the category known as embarrassingly parallel. And we can see that by looking there. You'll just see that there are multiple copies of Dash have been spawned off in the background. We're not using any fancy libraries like MPI or the grid. We're just firing off multiple copies of Dash, but keeping things under the control of this grid batch file. And you basically get a linear speed up with number of cores. And in the context of the amount of memory that you need to do this, it's absolutely nothing. In fact, the particular version of Dash that it invokes is even faster than the GUI version. It's a stripped-down version, and because it doesn't have the overhead of updating the GUI, it runs about 10% faster. So if you have a copy of Dash and you have a multi-core machine, it's well worth investigating. So I will leave that grinding away, and I will thank you very much for your attention.
Thank you, Ken. That was a very beautiful